Okay, so this workshop will try to illustrate some resources that you can obtain from the internet, and also I will illustrate a very important technique in the deep learning, which is we call the transfer learning. Means that we use the model that has been trained in other data sets, then we can use that model to reduce our training time in the new data. So, so this workshop, I will also provide you a smaller scale pneumonia data set for you to learn how this deep learning can help detect pneumonia. So one of the largest JSS-ray resources that you can find on the internet is from the National Institute of Health in the United States. And the NIH Clinical Center has released over 100,000 anonymized JSS-ray images and their corresponding labels to the scientific community. So, with the registration and the validation of your account, then you can download this database for the research and the clinical research purpose. So I think this is one of the great steps to in the medical fields to advance machine learning, because for any machine learning algorithms, it requires large amount of data. So data is everything. If you have no data, then there's almost no way to develop a meaningful algorithm at this time. So these JSS-ray images will be very valuable for any scientist, the data scientist or clinical scientist to develop and JSS-ray algorithms. So these images came from more than 30,000 patients, including many with advanced lung disease. So I think this is very valuable. You can try to download for yourself if you are interested in developing the algorithm to reading the X-ray, JSS-ray. And also, another resource for the medical images is the RSNA, which is the Radiological Society of North America. This, the Medical Society of the Radiology, is the largest one in the world for the radiologist. So every year they will hold a large conference in Chicago to gather more than 50,000 of the attendees from the world. And beginning in 2017, the RSNA has released each year special challenges regarding topics in radiology. For example, in 2017, the RSNA released a bone age prediction data. So, because in the pediatric, there's a transition from the pediatric, the childhood, to the adolescence, and in that transitions, our bone will begin to elongate. To extend it in its length, so the children will grow higher and higher, and there's also other corresponding change in the bone structures. So it is very important to know the bone ages to justify the progress of the pubic age. So this is the interesting challenges, and you can still download the data at this time. And in the 2018, RSNA challenges is the pneumonia. So you can you can find out the relevant data on the RSNA websites. And also in the last year, in the 2019, the RSNA challenges is about the brain hemorrhage detections. So so that's one of the another important topics in the neurology and neurosurgery. And so I believe this year the RSNA will also release a special challenges. I think this is really a great steps for anyone interested in the digital medicine to explore these different topics and to improve our medical care. So if you look on the internet, you can type in RSNA and pneumonia, then you will find this page. So RSNA already collaborate with the CAGO to hold the competition each year. So this is the competition held in 2018 that is try to ask a question: can you build an algorithm that automatically detects potential pneumonia cases? So in these competitions, we need to build an algorithm to detect a visual signal for pneumonia in the medical images. That means we need to identify the pneumonia, we also need to identify the locations of pneumonia. For example, if the pneumonia occurred in the left or right part of the lung. So it is the priced competitions, and it attracts lots of the people, and so I think it's the great the resources that you can explore. And these data sets is actually from the National Institute of the Health. So they try to do a very sophisticated the labeling. So we need to thanks to these radiologists to help to label these chest X-ray images, and not only the diagnosis, but they also try to label the locations of the pneumonia. And this is a very tedious work, and without their efforts, then we have no data to train our model. And another resource is at the Stanford University. So Stanford is very famous for is the pioneer research in the visual imaging deep learning. For example, the ImageNet, and also for they construct the resources which is called the chessboard that provide also a large number of the chest X-ray images containing different types of the diagnosis. So I show you this diagram to show the difficulties of the chest X-ray algorithms. That in the previous challenges, we only need to identify the pneumonia, but actually pneumonia is only just one of the diagnoses you need to differentiate in the chest X-ray images. And there are other diagnoses you need to differentiate from on these two-dimensional images. For example, for each X-ray image, you need to determine several possible direction of the abnormal findings. For example, if the heart is enlarged, and if there was an abnormal pleural findings, like pleural effusion or pneumothorax, and also if there is any lung opacity, which can lead to the diagnosis of edema, consolidations, pneumonia, lesions, or atelectasis. And also if there's a bone fractures, and if there's once you make sure there was no these findings, and then you can make judgment that there was no findings in these chest X-ray images. So I provide the internet link in these slides for you to explore this data set. And so for this model, then we need to develop very sophisticated algorithms. So this is one of the example using deep learning to develop these very complex models. So for any trace array images, so this is the using the concept of the transfer learning. Then we use the pre-trained models. For example, the AlexNet, the GoogleNet, or the VGGNet, or ResNet. And these models has been trained using ImageNet, which is the large collections of the real-world object in which contains the hundreds of thousands of the images, and they already use lots of the computation time to train this model to identify the objects, for example, from the very simple one like trees, flowers, cats, dog, to a complex one like a flag or traffic signs or different words. So using these pre-trained models, our hypothesis is that because the model itself can already identify some object in the real world. So it's just like a human baby. It can already see and identify lots of things in the world. So ideally, if we learn how to see this world, then we should be able to identify abnormal findings in a trace array. So the idea of the transfer learning is to use these pre-trained models that, assuming they already have some intelligence, and then we can use that intelligence to learn new things and to reduce our learning time. Okay, so that is the concept of transfer learning I want to show you in this workshop. So in these models, when we use these pre-trained models to train how to see a certain diagnosis in a trace array, then we will try to visualize the transition layers, which is the convolution layers, and to see what does the model see in the trace array images if they already correctly identify the abnormality. For example, if you train this pre-trained model to see the atelectasis, then you will try to visualize the results from these transition layers. You can see that, okay, this heat map is the transition layers, and you can see this heat map in atelectasis, which shows how models see these images, and also the diffusion. You can see that the model indeed see the diffusion in the coastal phrenic angles, and also likewise the mass. So this is the general architectures of the deep learning models when it is applied to the trace array images. And I also want to show you the latest advancement in this COVID-19 pandemic time. So the COVID-19 is one of the major symptoms or the resulting condition is the pneumonia. And although not every people infected with COVID-19 has pneumonia, but the pneumonia is still one of the condition we need to look for and be very cautious for these conditions. So it is still has very valuable to use the machine learning algorithms to identify the pneumonia in the COVID-19 cases. And in these papers, they already developed an algorithm using the pre-trained models, for example, the VGG19s and MobileNet, and to make a binary class or multi-class classifications of COVID-19 pneumonia and achieve a very good sensitivity and specificity and also the accuracy. So, so you can see that this is paper published in the early phase of the pandemic. So at that time, the case is still few, but nowadays that we already have lots of the pneumonia images, but just all from the victims of the COVID-19. So it is really sad, but it is really a timing that we need to develop practical algorithms. Okay, this is another paper that is, the title is Diagnosing COVID-19 Pneumonia from X-ray and also the CT images using deep learning and transfer learning algorithms. So again, the transfer learning is a very important techniques because we can use pre-trained model to reduce the training time. If you want to retrain model initialize parameters using the same models, it will take lots of time to finish the training. Maybe you need to take several days to finish the training. So in this paper, they also achieve high accuracies on the chest X-ray and also the CT images. And this is one of the applications proposed on the internet. It's called MedChecks. It's an e-alert system for automatically detecting pneumonia from the chest X-ray images. And they use the machine learning algorithms, pre-trained models, and also already developed a web-based platform to diagnose the pneumonia. And we also developed a cloud-based X-ray image platform in Digital Medicine Center at the National Yang-Ming University. And so I will illustrate this platform later, but just show you the layout of our platform. So you can just drag any images on this platform. Then not only you can browse these chest X-ray images, but also the model will return the diagnosis from these images and also try to give a tentative assessments and try to give whether there's a pneumonia and whether there's a presence of the lung fibrosis and whether there's a pleural effusions and also whether there's what about the heart size. So in this case, there is a pneumonia, there is a blunting in the coastal phrenic angle, so it means that there is a pleural effusions, and also there's maybe there's a lung fibrosis because of very severe lung infections. And also in the scope of the whole world, and there are many teams that are trying to develop practical applications of the machine learning in the X-ray or CT images. So this is one of the application called infravisions. They can identify the objects in the CT scans in the lung fields and to identify the mass or pneumonia lesions. And this is also a company from China. They already developed an algorithm to also to make a diagnosis of the CT images. But I need to emphasize that in the paper of New England Journal of Medicine in February, then we need to see that for the patients, all patients, there's the percentage of abnormalities on chest radiograph is only 60%. And means that if you only use chest X-ray images, you could only find 60% of the people has the abnormalities. So it means that you will miss the other 40% if you just based on X-ray images. However, if you can that patient to do the CT images, chest CT images, then this abnormality rate will increase to the 86%. Means that using CT it is more sensitive to detect abnormality in the case of the COVID-19 or SARS-CoV-2. And so that's why in many countries they already adopted CT as a standard procedure to evaluate the lung conditions in the COVID-19 victims. Okay, so in this workshop, the data we provided is from the RSNA pneumonia detection challenge. And as I said, this challenge is to for everyone to build an algorithm that can automatically detect potential pneumonia cases. And also, the challenge also want to develop an algorithm can locate the actual the location of the pneumonia. So the original training data and testing data are very large. So I already randomly select a subset of the data from these challenges that compile data contained only 1,000 cases with pneumonia versus 1,000 without pneumonia. So I need to emphasize that for those images without pneumonia doesn't necessarily means that there was no other findings, but there was no pneumonia in that chest X-ray images. And these images comes from large collection of the patients that have different kind of chest lung disease. So you will see that the image contains maybe there's a children's X-ray images, adults, older people's. Although there was no demographic information, but you can see different size of the lung and chest cavity in different files. And also you will see different imaging conditions like PA views, posterior to anterior views, or anterior to posterior views for supine, standing, etc. So it is indeed very challenging, but it's very fun. And all images were stored in a DICOM image format. So here I just open the MATLAB platform and show you to take a look at the data set. So I will provide a compressed file called pneumonia.zip. So when you unzip this file, you will see a pneumonia folders, and if you dive into the folders, you will see there are two folders. One is a 0 and the other is 1. So this is I call this AI ready data set. So the AI ready does not mean that it will generate a very good model, but it just means that all data already structuralized into the specific folders and categories that can help or facilitate the training progress. So if you just open this coding.txt, you will see that the 0 means non-pneumonia and the 1 is represent the cases with pneumonia. Okay, so when you click into the 0 folder, you will find there are 1,000 DICOM images, which has extension of .dcm, and also likewise in the folder 1, there are also 1,000 DICOM images with pneumonia. Okay, so we will use this data set to learn how to use the transfer learning. So before we work on the transfer learning, I want to show you the example provided in the MATLAB to see how does it work. Okay, so here I just show you the browsers using Chrome, and you can just type the MATLAB transfer learning examples. Then the Google should show you the result here, the transfer learning using AlexNet. So this is one of the example provided by the MATLAB to show how to do the transfer learning. So just take a little bit time to load the website. Okay, so here you can see that it has some explanations. Okay, so the AlexNet has been trained on over 1 million images and can classify images into 1,000 object categories. So this AlexNet is based on the ImageNet data. And these 1,000 object categories include keyboard, a coffee mug, pencil, and many animals. And so the network has learned rich features representations for a wide range of images. And so the ideas of transfer learning is that you can load pre-trained network and replace the final layers corresponding to your data. Then you can use these modified the network to do the training on your data. Then because these pre-trained network already identify features that related to pre-trained images. So ideally, you should be able to see something important in the new images, and so you can reduce the training time. You don't have to train from the beginning. You can train based on the established the training result. So this is the idea of the transfer learning. And here the MATLAB provide a simple example. So for example, here you can just follow these codes. So for example, I just follow the code here. And I will just switch to the MATLAB and just paste the code here. Okay, so you will load up the default data into these folders. I should move to the other folder, but anyway, I just make an example. I will delete my files later. And then you will see that in the MATLAB file, it shows the IMDS. So it's the imaging store variables, imaging data store variables. If you double click that, then it will contain the 75 cells and with the labels. So for example, it has the cap, cube, playing cards, screwdriver, torch, etc. And so our goal is to use the AlexNet to do the training. So here I just try to divide the label into the training and the testing data. Okay, and then using this small data set, we just randomly show the 20 images, sample images. So the first line, I just count the number of labels and to randomly pick up the 16 images and to show these 16 images using a loop command. Okay, so I just paste this into the MATLAB. So you will do a subplot and show the different images randomly pick up from the data store. Okay, so just close this window, and the next thing is try to load the pre-trained network. So I just type the net equals to AlexNet. Okay, so you can see that when I try to do this, the MATLAB returns an error message that LS requires a neural network toolbox model for Alex network support package To install the support package, use the add-on explorer. So I just click on this one. So no worry that when you see the same message. Okay, so I need to install this the package, and you will show up you need to enter your account information. So because you are affiliated with the National Yang Ming University, so you should have a license to enter the required information. So I will just enter this information, then download and install the toolbox.
Okay, so after you enter the credential of your account and accept the license, then you should see the progress window that's showing the progress of the installation progress, including the downloading the toolbox. Then after completing these steps, then you should be able to return to the MATLAB platform. So now that you can use this net equals to AlexNet, then paste into the MATLAB, there should be no problem here. Alright, so we already load AlexNet into the net variable. So in the right, you can see that there is a net variable called the series network. And if you double click on this net variable, you should be able to see the 25 layers in this network. Then including, you can see the first layer is the image input layer, and then follows by several repetition of convolution, ReLU, and normalization, max pooling, etc. So there are several layers of convolution and max pooling layers, but in the end of this neural network model, it's always connected to the fully connected layers and softmax layer and the classification output layer. So these three are important the layers that is determine the output of your neural network. So in the transfer learning, that we are going to replace these layers according to your data. So and also we need to specify the image input layer because the input image size might be different from your trained model. So we need to modify the first and the final layers. Okay, so let's go back to the tutorial, and so you can see that here you can analyze the network. Here, then you will see a window pop up here. So this is the full information about the deep learning neural network architectures. So in the left, you can see the different layers. You can click on each one and see the specification of these layers. For example, if you click on the data, which is the image input layer, it shows the activations is 227 by 227 by 3. Means that the input images has the dimension of 227 by 227 pixels, but because it is color images, so there are 3 layers, including the blue, green, and red. Okay, so in the final layer, you can see that this classification output, but the most important layer is a probability layer. It's called a softmax. It outputs the probability of each classifications. So here, the pre-trained Alex model has the 1,000 classes. So this is the standard trained model from ImageNet, but we are going to use this for the transfer learning. So after examining these the 25 layers of the Alex network, then let's go back to this tutorial. It shows that in the first layer, as I said, the image input layer requires input image of size 227 by 227 by 3, where 3 is the number of color channels. So here it just show you how do you determine the size of the input layers. So I can just copy this comment and paste into MATLAB. It shows the input size equals to 227 by 227 by 3. And here is the important steps in the transfer learning. We need to replace the final layers because the last 3 layers of the pre-trained network are configured for 1,000 classes. So we need to reconfigure these final layers. So we need to first extract the last 3. We first extract the all network layers except the last 3. So from the first to except the last 3 layers. Okay. So the end means the end, n minus 3 means that we need to extract layers from 1 to the layers excluding the last 3 layers. So I just copy this into the MATLAB and paste into and see, just assign the models to the layer transfer. Then here we need to determine how many classification or how many classes in our new data. So we need to calculate the number of categories. Here the number of classes is 5. Then we will just modify the new classification layers with the number of classes. So here we will recreate the layers of the neural network. So the first we need to preserve the layers transfer. We need then we add the fully connected layers with the new number of the classes, and then we follow by the softmax layers and output of the classification layer. So we just combine these things and paste into the MATLAB. Okay, then we can train the network. So here there's also other things we need to do some pre-processing, because the input images are 2027 by 2027 by 3, but however the new data, the image is not in this dimension. So we need to resize the input images according to our neural network models. You might be asking that why don't we just change the parameters in the neural network? And the simple answer is that because this is pre-trained neural network. So you can see that each weight in each layer is configured according to the input image data. So if you change these dimensions, it will affect the resulting configuration in the following layers. So it's better that we just resize our input images, but not to change the parameters in your neural networks. So if you want to use a transfer learning, okay? So here, just the MATLAB gives you a simple explanation that if you want to resize the images, it has a very simple function for you to do this kind of things. It is called augmented image data store. So it can do the resize for you But I will show you later that it doesn't work in our trace X-ray data because we need uh, to read the images by the DICOM files. So we need to um, do different things in this step. Okay, so but for now we just follow the MATLAB tutorial and to resize the images. Okay, then we will resize the images with this command and assign the data to augmented image IMDS validations. Then we just give the neural network some default parameters. Then we can train these neural network models. Okay. Then it should pop up the training windows very soon. Okay, so you can see that it's quickly finished the training and the validation accuracy is 100%. So it's a very simple tutorial that then you can follow these things. I will not demonstrate this step, but you can, if you are interested, you can follow these things and you can try to predict the outcome based on the validation data and to plot a confusion matrix. Then also, if you are interested, you can also follow this step to show some images with their predicted labels. Okay, so this is a tutorial for the transfer learning, and the idea behind the transfer learning is that you can use the pre-trained model to classify the new data. So the idea is that because the pre-trained model has achieved very high accuracy on the trained images, and it should contain some ability to see certain features, then it will reduce the time of training in the new data. Okay, so we finished the tutorial on the transfer learning, but we still need to do something our pneumonia data. So remember in the last week's tutorial that we applied the simple CNN to the pathology data, and in that data we have the data format as the PNG files. So remember that I have provided a simple CNN code, so you just need to specify the image data store, and you can use the CNN functions to train your neural network. And in that tutorial, and because our the image format is PNG, and so the command here should be the .png. And you might be wondering that how about we just change it to .dcm, because so see if we can use the image to data store function to input our image data into the IMDS variables using these DCM extensions. So you can try this, but I think it will result in an error like this one. Okay, so here you can see that when I try to execute the image data store functions using the present working directories and .dcm, you can see that it's error using image data store functions. It has this error using read functions, read data store image function to handle for file. So it means that we need to change our read functions and to for our data stores. So what does that mean? So let's take a look. So for example, if we just try to look at the documentation of the read data store, image data store functions, image data store functions, then you can see that you need to specify the location, name, values, and also the reading functions here. So the reading function here, you can specify the custom reader. So it means that when you do, for example, when you want to read a specific files into the MATLAB, then you need to specify a function to read those files. And for the default, you can read the image files, but you cannot read the DICOM files. So that's why we need to change that function in the read FCN parameters. So no worries, that will provide you customized functions, which I call the DCM to data store functions. So in these functions, I just similar to the image to data store functions, I just try to specify the read function as a DICOM read. So remember that in the first workshop, I used the DICOM read to import the DICOM files into the MATLAB. So here, I just use the customized read functions, then as the input to use the image data store functions. So you can safely just follow these command lines, and I just change this to the present working directory and file extension as the .dcm, and the label options. So here I just put 0 here. So you can see that the resulting variable here is IMDS. It has 2,000 cells, files, and it has a label from 0 to 1. Okay, but here the difference that you can see the read function is the DICOM read, which is the default function for reading DICOM images. Okay, so now we use the DCM to data store functions to create our IMDS data store variable. But not so happy, because when you execute this line, you will encounter an error when you do the CNN training. It is because that the input image size is still large. That because the data, the DICOM image I provided to you had the size of the 1024 by 1024 pixels, and that is too large for our CNN model, because remember our CNN model has the inputs around like 30 to 50 pixels by the dimensions. So we need to rescale our input X-ray images. So you might be wondering that for our human, we want to see every detail of the chest X-ray images. Then how if we just resized our images, is that possible we could lose some detail about that chest X-ray images? I think that is true, but remember that the computer is working on the pixel as a very small scale data, so it doesn't need a very detailed the image data that to see the features. And the most importantly, because if you use a large input size, then certainly you need many feature extraction process to extract the necessary features, and it doesn't work in our small CNN model. So we need to resize our DCM to data store to modify the code to resize the DICOM images. Okay, so back to the MATLAB, you can see here that the DCM to data store functions, I have another line here showing using the customized read functions as a DICOM reprocess. So a preprocess. So the DICOM preprocess functions is very simple. You just read the DICOM files into the DCM variables and use the IM resize to resize the images. So the IM resize functions will resize the DCM functions into the 50 by 50 pixels output. So I use these functions as a customized read functions, and then we can run this CNN model. So I already run this for you, and now that I run this CNN model for more than 8 minutes, it doesn't finish yet, so that's okay. So it finished now. So you can see that use this CNN model, we can achieve the 64.33% accuracy in the validation data. Then you can clearly see that although during the training progress, the training accuracy has approached to like 80%, but the validation accuracy still keep around at 60%. So that's a kind of overfitting, and there are many reasons for the overfitting. The one of the reason maybe just the resize images doesn't work, or also we need more features to learn the data, and probably the features we capture in the CNN model doesn't work on the validation data, so you will see the overfitting in this case. But anyway, here is just showing how do we use the simple CNN model to do the pneumonia classifications. It is difficult than the pathology image analysis, and so maybe we need more sophisticated deep learning models using transfer learning. Okay, so I think the key point for running the CNN model in these pneumonia data is that you need to pre-process the DICOM files and to reduce the dimensionality of the image size to 50 by 50, or even by smaller the data size. But you can try yourself to see if you can improve the accuracy based on the simple CNN model. But for the next, then we need to learn how to apply the AlexNet to the pneumonia data. And the key point is that you need to resize the DICOM images according to the AlexNet. So remember, in the AlexNet, the input size is the 227 by 227 by 3. So not only you need to resize the DICOM images, you need to triple the one channel DICOM data to the 3 channels DICOM data. So before you can you're running the AlexNet, you need to do these 2 pre-processing steps to make sure you can use the AlexNet to run the transfer learning. Okay, so here the first thing we need to do is to modify our DICOM pre-process code. So remember, in the first line we use the DICOM read to input our DICOM files, and in the following lines then we do the image resize. So in the previous example that I resized the DICOM image to the 50 by 50, but here because I want to use the AlexNet, so I want to resize our DICOM image to the 227 by 227. And because our DICOM is the gray image files, so it has only 1 channel, which means it has only black and white colors. And so for the input images in our AlexNet, it requires the 3 channels color images, but because we don't have the color images, we just to triple our images to the 3 dimensions. So we use the concat function, which is cat functions, to combine these DCN resize the matrix into the 3 channels data here. So the output is the 3 channels. Okay, so we can use these as our reading functions to read our image data as the DICOM format. So how about we just to read these functions, so you can see the IMDS here is still the 2000 files, and the read function is the DICOM preprocess. And now we need to go back to our transfer learning. So you can see that we can follow this step is that we already to try to load the AlexNet here. Okay. Then we skip the analyze network step because we already know the architectures, and we know that for the first input we don't need to change anything, but we need to change the final 3 layers. So because we already modify our DICOM read preprocessing functions to resize the DICOM image to 2027 by 2027 by 3. And so here, then we need to follow this line. We need to copy the main structures of the AlexNet, and then we need to determine how many classes in our new data, which, I need to specify the training and the testing data here. Okay. So we need to create the IMDS train and IMDS validation, and still use the DICOM preprocess functions. Then we will determine the number of classes in the validation data. So there is a training data. So there are 2 classes here. Then we can specify the layers here. Okay. Then we'll skip this one and to do the training. But remember here, because in the tutorial they try to resize the input images, so they resize the images using augmented image data store functions. But for our data, we only use our image IMDS trend data. So we need to modify this line when we do the training. But before that, we need to specify the options here. But remember that we need to take out this AUG here, so that we can do make sure that our validation is in using this IMDS validation. And likewise, we need to modify this line to take out the AUG because we didn't use the augmented IMDS store functions. Okay, so you start the training windows. It takes some time actually because the file size is larger. So imagine that if you have large training files, then you will take a significant time to read files. And here you can see there's 840 iterations here. So it's a long process. I will just pause the video here and to wait until the finish of the training. Okay, so the training progress here is very long, and so I just show you the one of the progress here, just running for almost 15 minutes. And actually you can see that this is a common scenario in the deep learning, that you need a very long time, and there is a gradual increase in the accuracy, although so far the validation accuracy is still approaching 60%, approaching 70%. but it went through up and down progress, and in the long run, it will still goes up gradually, but it will take a very long time to achieve that accuracy. So um, for the even deeper neural network, it will take a very long time to achieve the final accuracy. So, but be patient. But I will stop here and to show my final slide here, so you can see the accuracy goes up again. So there are many pre-trained models in the MATLAB, and these models include ResNet 18, ResNet 50, GoogleNet, Inception V3, DenseNet 201, and etc. Or for example, VGG 16, VGG 19. So these are the deep learning CNN models that has been proposed in the past years, and they already trained on a large collection of the images. Then, so it is a current trend that if you want to do the medical image analysis, then you can adopt these pre-trained model in MATLAB to do the learning on your neural network, your medical data. So I think this will conclude this week's workshop, and I hope you learned more about how to do the deep learning in the medical imaging data. So in the next week, we will move on to the brain CT image. It is more challenging, and but it is fun. But the principle is the same. So we will still explore how to use the simple model and the pre-trained model to do the training on the brain CT data, or even difficult is MRI imaging data. Okay, so for now I will just stop here and hope you enjoy the course. Bye bye.